Good afternoon. As promised, I think I spelled this wrong right off the bat. I'm sorry about that. So, as promised, I'm going to be working some problems from section 13. I have a total of 4 problems laid out here that we're going to think through and hopefully work through. Once again, little disclaimer, I am not a teacher for this course. I am myself still learning this course. These just help me study, and maybe we could learn something along the way together. So these are all coming out of Munkres' Topology 2nd edition. This is coming from section 13 exercises. So the first one that we're going to be looking at is prove that the co-countable, so this T sub C, this is the co-countable topology, is defined as the collection of sets U belonging to X such that X less U is countable, or all of X is a topology on X. So we want to prove that that's a topology. And is the collection over here, this new one, an infinite, empty, or all of X, a topology on X? So let's start with the co-countable one right here. So the first thing that stands out to me here is we need to check off our 3 boxes for a topology here. So the empty set and the entire set must be contained inside of my collection of sets. We need to have the arbitrary union of sets exist inside of my topology, and then the finite intersection needs to exist inside of there as well. So the first thing that stands out to me in the co-countable topology is A, X exists inside of it, because our construction right here says or all of X. So that means X has to be contained. X is contained in this collection. So that checks that first box, and then we actually also know that the empty set must also exist inside of here because the empty set is countable. And because it's countable, that means it exists inside of the co-countable collection. So we also know that the, go back to latex here, so we have the empty set is also in this guy right here. So that checks off our first box. So we know the empty set and the entire space are included inside of this collection. So the next thing we need to know is arbitrary unions, right? So if I union absolutely everything together and get back my entire space, well, we already know that that space is contained inside of here, right? So we're more concerned with arbitrary unions of indexed elements, which is our use of alphas, right? But in this particular case, we kind of already know that, and this is stemming from analysis, and I believe this comes from section 9 or 10 in the book, is that the union of countable sets is itself countable. So I'll write that out. Union of countable sets is countable. So it doesn't matter how many unions I take. I can take infinitely many unions in this particular set, but the union of countable sets is countable. So the second condition is met. So now we have the second condition that the arbitrary union of sets inside of my collection land back inside of my collection, right? And then lastly, we need finite intersections, right? I need to make sure that the finite intersections of arbitrary sets indexed sets inside of my collection land back inside of my collection, right? Well, in this particular instance, the intersection of a countable set with another countable set is also countable. So what we can say here is the finite intersection of countable sets is countable. So that checks off our third box. So what we can do is we conclude that the co-countable topology is in fact a topology, is a topological, is a topology. I'll just say is a topology. Okay, now the next portion of this problem that we are asked is that is the collection of this T sub infinite, where x less u is either infinite, empty, or all of x, is that a topology on a set X? So right off the bat, we can see that the empty set and X is included in there, so that definitely checks off our first box there. But what I want to look at here is I'm going to now look at the unions. So I'm going to make the claim that this does not, does not form a topology on X, and I'm going to give my reason for that. So I'm going to say let X equal the interval from -1 to 1, and then I'm going to have a indexed set of use. Sorry, I'm still in LaTeX. That's why. I'll flip back to Unicode here. So -1 to 1, and I will let a indexed set of u1 be the half open interval from -1 to 0, and I'm going to let a u2, a second indexed set, be the half open interval from 0 to 1. Well, once again, the arbitrary union of these indexed sets needs to once again fall back inside of it. Now, the problem that we run into here is that, so I'll say then, what we get is that if I take x, if I take x and then subtract it, oh my gosh, please, 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 please. So if we take x and we less it from the union of u1, and I believe it is just union. It's not. It's not. Okay, let's backtrack a little bit here. Let's go ahead and union it, and I'm not going to bother with the u1 and u2. You get the gist. If I were to take x less that, then what I wind up getting is that this will actually equal a singleton of 0. Now, this singleton of 0, it is not infinite, it is not empty, nor it is all of x. So what we get is we get a contradiction at the second step of our process, right? So what we've now shown is that the arbitrary union of sets does not fall back inside of my collection. So we say that this is not a topology on a set X. So that wraps it up for 13.3. Going to jump down to 13.4 here. So this one's going to be a little bit on the lengthier side, maybe not like a ton. So we have a family of topologies on X. So now we have a collection of a collection is how you can think about it. But a family is essentially a collection of a collection, right? So we want to show that the intersection of these collections is a topology on X. And then what we want to check is, and I know it kind of like cut off here, but this is the union of those. Does that form a topology on X? And that's going to be our first portion of this question. We have an A, B, and C. So first thing we can see is just by construction, we know that the empty set and X must be in T alpha. Must be in, or must be in all T alpha, right? We can guarantee that because it told us that all of these are topologies, and for something to be a topology, it has to have the empty set and the entire space inside of it. So by definition, it has to exist inside of that intersection. So we say, so exist in this intersection over here, right? So once again, that's just due to the fact that these are all topologies, so they exist in all of the topologies, right? Now the next thing we need to look at is arbitrary intersections, right? So let's go ahead and say suppose, let's go ahead and mathcal this. Let's call it A. So like let's say A in, let's do mathcal. Oops. I don't know why it's not registering the alpha. It was doing that earlier to me, and I'm not entirely sure why. It's giving me trouble there. But let's assume that we have a collection A that belongs to the intersection. No, sorry, I guess I should have just done this instead of going through that trouble. So let's say that we have a collection of sets that is an element of these intersections, right? So I have all of these sets, right? And I'm going to find all the ones they have in common, and I'm going to create a collection of that, right? So let's go ahead and grab that collection. And then let's also consider any, I'm going to go ahead and just kind of steal this guy right here. I'm going to be changing the variable just a little bit here. So instead of T alpha, I'm going to do T beta. So we're just going to consider any topological space now, beta, and any, let's go ahead and do A in mathcal, and just any set that's inside of that subcollection, right? So I'm just kind of like setting myself up to run through this proof here. How I built this out is that we know, and I guess I should probably specify that T beta is part of my intersections of T alpha. Let's say that T beta is an element of this family. It's an indexed part of this family, right? It's just a random topology inside of that family of topologies. So what we know here is that A, like our A, must be inside of this one, must be inside of at least this random topological space, right? So we know that A is in this guy right here, right? A must be in, if A is a set that's composed of these intersections, then we know that A has to exist in all of these index families topology. So if I just pick a random one, then I know that A has to be inside of that random one. So what we can say here is that it follows, it should follow here that our collection A is a subset of this topology. So I will say that mathcal A subset of our topology, and specifically our topology beta. So let me, I don't know why it didn't bring that along with it. Do I have something I just copy and paste real quick? Of course I do not. Subset, and I hate that the subset just adds this random space in Word. It's so annoying. I know I said that in the past couple videos and I just do nothing about it, but what you gonna do? Okay, so A, our collection A is a subset of that index topology. So the union of those, so I'll go ahead and just kind of do a little copy paste action here. So the union of these random collections must also exist inside of there. And that's due to the fact, and that's since this guy is a topological space. So once again, we're kind of using the fact that these are topological spaces. So I know that the arbitrary unions have to be inside of these topological spaces because we've already guaranteed that they're topologies, right? So I can say that the arbitrary union of these is inside of there, and that's due to the fact that it's a topological space. And so what that means is that the arbitrary unions must also be in T alpha. And so that really concludes our second portion here, where we needed to show that the arbitrary union of, in this case, it would be collections, which is why we're kind of using this collection A to prove that. We're showing that the arbitrary union of these collections lies inside of this family, right? Okay, and the last thing we need to show here is we need to show that indexed families lie back inside of it. So now I'll say suppose, and I'll just flip back to Unicode for this one to make it just easy on myself here, allegedly. Unicode. Okay, here we go. So U1 and comma dot dot dot, and then let's get a UN. So I have an arbitrary just indexed set here, right? Let's go ahead and say in, and this is going to be in my T alpha, elements of T alpha, right? And then once again, let's go ahead and consider any TB. So we'll say, and oops, da, 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 and consider any topological beta, so just a random family, sorry, a random topological space inside of there, any to be precise. And we'll say such that that here, let me write it like this. So it would be u sub I, so just a random one is in, that they exist inside of here, right? So these sets exist inside of these of this indexed topological space, right? And then I should be a little bit more verbose, so I'll say for I equals 1 comma dot 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 comma in, and this is just to kind of like set up my index here. I do know that indexes really do matter, so we're just going to kind of keep rolling with that. So this first one, we're going to go ahead and keep continuing. So we can say that since this guy right here is a topology, so since that guy is a topology, let's think through. Since it's a topology, then the finite intersections must exist inside of it. So I'm going to go ahead and, where would that be inside of here? Not there. I think it'd be under large operator. Yeah, unions and intersections. Yeah. So this would be I equals 1 to n of my u sub i's, and that needs to be in that needs to be inside of this topological space, because once again, since it's a topological space, we can guarantee that the finite intersection of these sets has to be inside of there. So we can actually conclude that, I'll just go ahead and basically copy and paste this over here for ease on my end. So we can guarantee that since we know this for this random one, in this random topological, this random topology on X, it will go for all of those topologies on X. And we have now proven that the family of topologies on X is itself a topology. The intersection of those is a topology. Now we ask the question, is the union of them a topology on X? To which I say it is not necessarily a topology. It could be, but not always a topology. And I will give a pretty easy counter example for this. So I'll just say given x equals a comma b comma c. So we're going to go back to that very basic example, and we'll go ahead and do, I'm just going to steal these guys again. Actually, I think I already have it locked and loaded. Oh yeah. So let's just say T1 is equal to the empty set x and b. I typed C, I meant x. And then let's do T sub 2 is equal to the empty set again. Empty set, there we go. X and A. What we get here is, let's go ahead and do the union of the two. So then let's go ahead and do the union of T1 union T2. Well, that's going to equal, we're going to have the empty set in there. We are also going to have x, we are going to have a singleton, and then b singleton, and then we'll close that out, right? Now, the problem we run into here is that this fails the definition of a topology, right? Because if I were to take the union of a and b, well, that doesn't land me back inside of this collection. So we have now failed the definition for a topology. So the union, so while the intersection of a family of topologies on X is a topology on X, the union is not necessarily one. Now that doesn't mean it can't be, it's just not always the case, right? What we want to show here on the second one is there's a unique smallest topology on X containing all the collections, and a unique largest topology contained in all of them as well. This one is definitely more involved than the others. I think 13.6 is pretty quick and easy, and then 13.8 I believe is also like relatively quick-ish. Okay, so there's a couple things that like stand out to me. So containing all the collections, T alpha, right? So something we just showed is that the union of topological spaces does not necessarily form a topological space itself, but what we can do is we know that this guy right here, it does form, I guess I should start, does not necessarily topology on X, but it does form a subbasis, since if I were to take the the union of this guy, it does equal the entire space X. And so, therefore it forms the subbasis topology. So if we think back to our definition of a subbasis, right, it was the union of those covers the entire space. Well, the union of this union of collections will equal my entire space X, so it forms a subbasis, and therefore it forms the subbasis topology. And what I'm going to claim here is that this subbasis topology is the smallest. Now, once again, we're getting into the idea of smallest and largest. Once again, correlate that with finer and coarser. Coarser being smaller and finer being larger. Okay, so I'm going to claim that this subbasis topology is the finest topology that I can create here. So the first things first is that we need to talk about the uniqueness portion of it because I need to address that. If I have this topology, and actually let me go ahead and give it a name. I'm going to go ahead and just call it T sub S for subbasis. And okay, so if I were to have some other topology, T1, for example, well, if T1 were the smallest, then T1 would have to be a subset of TS, and TS would have to be a subset of T1, so TS would just have to equal T1 anyway. So uniqueness is pretty straightforward in this case. Let's go ahead and say that for each alpha, let, and then I'll have to switch back to latex here. Let a collection, a basis, and then let me go back and flip back to Unicode. Okay, let this guy right here be a basis. Let's let it be a basis for my topology, T alpha. So now let's say we're going to go ahead and, once again, TS is the topology generated by the subbasis. So what we can say is, we can say, so I need to go back to latex. So my subbasis here should equal, and in this particular instance, I'll go ahead and just stick with union, and I will copy and paste into here. So the union of those B alphas. So this is the subbasis that's generating the subbasis topology. Sorry, let me be very clear about that. So I'm saying that S is the subbasis, and the subbasis topology is generated by the union of my collection B alpha in this particular instance. Then sorry, I am checking my notes real quick. Then the collection B of all finite intersections of elements. Okay, yeah. So then what we can have here is /mathcal then my collection B of all finite intersections of elements of S of my subbasis is a basis for TS. And where did I have called TS? Right here. And so clearly, what we now have is that T. Did I write that right? Yes, I did write that right. So then clearly T alpha slash subset of TS for all alpha. So let's go ahead and kind of roll this one back. So we first started with the union T alpha does not necessarily form a topology, but it does form a subbasis topology because the union of those unions of T alphas will give us the entire space, which is the definition of a subbasis topology, which we call TS. Now, we're going to go ahead and create an index alpha. So for each alpha, let a collection B sub alpha be a basis for a topology T alpha, right? So then the subbasis is the union of those bases. So then a collection B of all finite intersections of elements of my subbasis is a basis for that subbasis topology. And so what that means is that every T alpha will be a subset of my subbasis topology, meaning that the subbase topology is coarser than all of the other topologies that I can have. And so it is therefore smaller. Now, the next one, I believe, is, let me double check that I'm answering all the right things, and a unique largest collection. Okay, so I'm going to jump into the largest topology side of things, I believe. So, sorry, I am just reading my notes again. Okay, so for the largest topology, uniqueness follows. Um, And what I'm going to say is that from part A, our intersection will actually yield the finest topology. So we know that T is a topology by Sorry for the dead silence. I'm thinking through what I have written down to make sure I'm not saying the wrong thing. Okay, so I think how I thought about this was that the intersection of all topologies will give us our largest topology, so our finest topology. Um, we know that the intersection will be a subset of all T alphas, no matter what, right? Because uh, every single every single thing in there was a part of every T alpha in order for it to happen. Um, yeah, so I guess just thinking it through, to me, like right off the bat, I would just say that I would claim that the intersection from the previous part A up here is the largest topology since that topology a subset of all T alpha. So that would make sense to me because I want it to be finer, which means it needs to be a subset. But that subset is created by the intersection of all of those topologies. Well, then, if it's all of those, then that will have to be the largest one that I get out of it. And once again, this is contained in all T alpha. Okay, yes, this jives with how I'm thinking because it needs to be contained in all T alpha. So I can't just like pick out like the discrete topology from that family of topologies, right? Because unless that discrete topology is contained in every single one of them, then I can't say that that is the finest of them all. So the finest one is just going to be the one that has all of the commonalities between all of them. Cool. Okay, so going into problem C, we want to find the smallest topology and the largest topology. So this kind of follows from what we just showed in part B, honestly. The union here, sorry, we just showed that um, we just showed that the smallest is going to be the intersection of these. Hold on, let me just quick double check. So the smallest will be the union the smallest topology containing T1 and T2. Okay, yes, the smallest should be. I think I might have got it backwards in B. Did I get it backwards in B? The largest should be the finest. Sorry, I'm getting small and large mixed up in my own head here. So small should be the coarser one, and large should be the finer one because there's more. I'm going to double check the book real quick on that. Make sure I'm not spitting hoopla out into the world for no reason. Yeah, larger is finer, smaller is coarser. Okay, so the finest, so I'm just going to stick with finer and smaller, finer and coarser because that's what makes sense to me. So we just proved from part B that the finest topology is going to be the union of these topological spaces. So in this particular instance, the finest topology will be, so we're going to have the, sorry, let me go back to Unicode. So we're going to have the empty set X. We're going to have A, since that's there. I'm going to have A comma B, and then B comma C. And once again, I mean, you can do like a quick double check that this does form a topology here, right? It's pretty easy to check. And then we would say, and the coarsest topology will be just the intersection between the two. So I will have the empty set, I will have X, and I will just have A, which does in fact form a topology, right? All right, and now we're down to 13.6. So what we want to do here is we want to show that the topologies of the lower limit topology and the K topology on the reals are not comparable with one another. So this one, we kind of have like two different directions that we need to show here. We need to show that they are not subsets of one another, essentially. So I guess subcollections is what I should say instead of subsets. So let's go ahead and say let's go ahead and flip back to LaTeX, MathCal. And so let's let these two denote the topologies of, I guess I can just copy and paste that portion, and I'll say respectively, so that people are on the same page that that's what they represent. So let's say given a basis element, so given a basis element of, let's say 0, the closed interval, the half open interval 0 to 1 for the lower limit topology. So that's for the lower limit topology. The lower limit topology. So for TL, there does not exist a basis element for TK, for the collection K, containing 0 and contained in that interval, that half open interval 0 to 1. So what we know is that TL is not a subset of TK. So that's the first half of this bad boy. So kind of think through it here. So a basis element, so the basis of the lower limit topology is the half open interval AB, right, where A is less than B. So we have a basis element of that, which is the half open interval from 0 to 1. Now, there will not be a basis element for my K topology containing 0 that is also contained in that half open interval from 0 to 1. And that's because we just keep slashing all of those 1 over n's outside of that set. So I can't make it small enough to fit inside of this interval somewhere and be fully contained inside of it, right? Because that's what it means to be a subset, is that it's fully contained inside of there. So I have found an instance where I just can't fit something inside of it, right? Now, the other way around, so now given the basis element, let's say -1 to 1, less k, so remember k is just that 1 over n, where n is the naturals, and that's 4tk. There does not exist a basis element for TL containing 0 and contained in that interval, so -1, 1, less k. So in this instance, so TK is not a subset of TL. So since they are not subsets of one another, they cannot be comparable with one another. All right, lastly, we will look at 13.8. So part A, apply lemma 13.2. So just as a refresher of lemma 13.2 is right here. Let X be a topological space. Suppose that C is a collection of open sets X, such that for each open set U of X, each X in U, there's an element of the collection C, such that X belongs to the collection, which is a subset of U. Then that collection C is a basis for the topology of X. So that was lemma 13.2. To show that the countable collection, collection B of the open intervals AB, where A and B are rational, is a basis that generates the standard topology on R. So let me think through here. Okay, so let's go ahead and start making some definitions here. So like let's say let's let T be the standard topology on R. Okay, so we can first say clearly that B in this instance, so B is coarser than my topology T. So this one seems pretty straightforward to me. So once again, coarser means that T is a subset of my basis here, which is B. We are basically just taking, once again, the standard topology on R is just R itself, right? Like it's just the line R. Well, if I'm dividing it into a bunch of subsets of the open intervals A, B, well then that's going to be I can just pick an AB. Let me put it this way. I'll draw it out, kind of how I'm thinking about it. So the way I'm thinking about it is if I just have R, well, that's like singleton points, right? Like I have 1 and then like square root of 2 and so on and so forth, right? But if I use that basis B, well, now all of a sudden that's comprised of these intervals, right? So now I have a set in here of the interval that contains 1 and root 2 and so on and so forth, right? And so I'm essentially just drawing more brackets around these guys and dropping these middle brackets, right? So this is going to wind up being coarser because I can create the same thing, but with essentially less groups of brackets that I have to use. So clearly, that's why I'm saying that this is coarser than that. Now what we are going to do is we are going to let U in, we're going to create a set U that belongs inside of this collection T. We are also going to say and X in. So we're going to take a point X inside of that set U. So we say that then U contains an open interval with center X So U must have an open interval with center x, and since the rationals are dense in R, so since the rationals are dense in R with the standard topology, there exists a Q in the rationals, a point Q in the rationals, such that x must be in this interval right here, x minus q and x plus q, which is a subset of U. So what this shows is that T is coarser than my B in this particular setup. So we conclude that B must equal my collection T. Right? So since the rationals, we start off with a set that belongs to my collection T and just a point inside of that set. So U must contain an open interval with a center point at X. Now, since the rationals are dense in the reals with the standard topology, there exists some Q that I can create that interval. So basically, this is me centering that X inside of an interval that it belongs to U. And since I'm able to center it, it shows that T is coarser than whatever B I create. So basically, if I have that open interval AB, what I'm saying is I can create an interval outside of that AB that now contains that bigger portion of it, right? For that center point X. So we can say that that is coarser, but if each of them are coarser than the other, that means they have to be the same. Now for part B, we want to show that the collection of half-open intervals is a basis that generates a topology different from the lower limit topology. All right, so let's run through a contradiction here. This collection C, so I will say, so this collection C forms a basis for a topology on R. Now, what that topology is, it's not the lower limit topology, it's just a topology. It doesn't necessarily have a name to it. So let's go ahead and say consider some half-open interval R and S, where R is irrational and S is any real number. Let's just say any real number greater than R, right? So what we can say is then Rs is a basis element for as a basis element for the lower limit topology, because the lower limit topology is just these half-open intervals, right? But it is not a union of elements of C. of my collection C. So now let's say suppose that this R comma S, this half open interval of RS, is equal to an indexed union. So I'm going to index my union here of A sub alpha comma B sub alpha of this half open interval right here. And then we'll say for rationals, for the rationals A alpha and B alpha. So that means then our R has to be in that open interval, sorry, that half open interval, AB here. So it has to belong there. For some alpha, but since R is irrational, we must have that A sub alpha is less than R. But then what we get is we get A sub alpha is not in the half open interval of RS, which raises a contradiction to our original statement. So my collection, I didn't have it still saved. So my collection C is strictly coarser than RL. Okay, so let's kind of think through this again. So the collection forms a basis on the topology R, right? So like let's go ahead and just pick a half open interval where R is irrational and S is just any real number that's greater than R. So that half open interval RS will be a basis element for the lower limit topology, right? That's just fitting into the definition, but it's not a union of elements of C. Because C is such that A and B are rational, right? So since R is irrational, it can't fit inside of that collection C. So let's go ahead and suppose that basically we're proving that it's not a union, right? So like let's go ahead and suppose that that half open interval RS is a union of some sort of ABs coming from C, right? So that's where my indexes alpha are coming from. So that means R would have to belong to that half open interval of A alpha and B alpha for just some alpha, right? It needs to belong to one of those if it's comprised of the union, right? But since R is irrational, it must mean that A sub alpha is less than R. But that means A sub alpha can't belong to my interval RS, right? So we get a contradiction. So the collection C will be strictly coarser than the lower limit topology. And it's primarily because the lower limit topology, we're basically missing out on irrational values here. So it can't be the same thing. We can't form the same topology because we're missing stuff from the lower limit topology here, if that makes sense. Well, that's going to wrap up some section 13 exercises. There's quite a few more exercises in that section that I would implore you to try to work out.